Quantum wonders, unlocking the universe's smallest secrets. The end of certainty, when reality got weird. Imagine a universe that runs like a perfectly engineered clock. Every gear tooth meshes with predictable precision, every turn of the hand follows an undeniable law. In this universe, if you knew the exact position and speed of every single particle at one moment, you could, in theory, calculate its trajectory for all time, past, present, and future. No surprises, no mysteries. This was the triumphant vision of reality that reigned supreme at the close of the 19th century, a worldview shaped by centuries of scientific discovery and epitomized by the towering figures of Isaac Newton and James Clerk Maxwell. Newton's laws of motion and universal gravitation had revealed a profound order in the cosmos, explaining everything from the falling apple to the dance of the planets. The universe was a grand, deterministic machine, its operations laid bare by elegant mathematical equations. Light, electricity, and magnetism, once distinct phenomena, were beautifully unified by Maxwell's equations, showing light to be an electromagnetic wave rippling through space at an astonishing speed. It seemed that physics had truly reached its zenith. As the dawn of the 20th century approached, many leading scientists believed that all the fundamental laws had been discovered. All that remained, they thought, was to fill in the minor details, to make measurements with ever-increasing precision. Even Lord Kelvin, a brilliant physicist of his time, famously remarked in 1900 that there is nothing new to be discovered in physics now. All that remains is more and more precise measurement. He did, however, append a cautious note that two clouds lingered on the horizon: the problem of blackbody radiation and the perplexing results of the Michelson-Morley experiment, which ultimately led to Einstein's theory of relativity, a story for another time. Little did he know that these seemingly small clouds contained the seeds of a revolution that would shatter the classical worldview and usher in a new, profoundly strange understanding of reality itself. The first cracks emerged. The first cloud, one that challenged the very nature of energy and matter at the smallest scales, concerned how heated objects emit light. Imagine a piece of metal glowing red-hot, then orange, then white as its temperature increases. This is called blackbody radiation, an object that absorbs all radiation that falls on it, and then emits radiation based solely on its temperature. Physicists could easily observe the spectrum of light emitted by these objects, but they couldn't explain it using the established laws. Classical physics predicted that a hot object should emit an infinite amount of ultraviolet light and X-rays, a catastrophic flaw often called the ultraviolet catastrophe. Picture a bathtub being filled with water. Classical physics suggested that as you let the water drain, you should be able to collect an infinite amount of water, especially as you narrow the drain. The reality was that no matter how small the drain or how short the wavelength of light, only a finite amount of energy came out. Observations showed that the energy emitted by a heated object peaked at certain wavelengths and then rapidly dropped off, instead of skyrocketing into infinity. It was as if the universe had a built-in safety valve, preventing a runaway energy crisis. The theoretical predictions simply didn't match the experimental evidence. This was a deep, unsettling puzzle. Why wasn't the energy being radiated continuously across all wavelengths, as classical theory demanded? Then there was the photoelectric effect. This phenomenon, discovered in the late 19th century, involved shining light on a metal surface, which would then cause electrons to be ejected from that surface. It's the principle behind everything from automatic door sensors to solar cells. Classical physics, which viewed light as a continuous wave, predicted that the brighter the light, the more energetic the ejected electrons should be, and that any frequency of light, regardless of how low, would eventually eject electrons if it was bright enough. Think of it like trying to knock stones off a wall with ocean waves. Bigger waves, brighter light, should knock off more stones, and even small ripples, if they hit for long enough, should eventually dislodge a stone. But experiments showed something entirely different. Frequency mattered, not just brightness. Electrons were only ejected if the light had a frequency above a certain threshold, no matter how bright or intense the light was. If the light was below this frequency, even if it shone for hours and was incredibly intense, not a single electron would be freed. Instantaneous ejection. If the light was above the threshold frequency, electrons were ejected almost instantaneously, even in very dim light. There was no waiting time for energy to build up, as you'd expect from a continuous wave. Electron energy. The energy of the ejected electrons depended only on the frequency of the light, not its brightness. Brighter light above the threshold only ejected more electrons, not faster or more energetic ones. It was perplexing, akin to a vending machine that only accepts specific coins. No matter how many pennies you insert increased brightness, you won't get your soda. But if you put in just a single quarter, the minimum frequency, the soda instantly drops, and putting in more quarters, higher frequency, gives you a more premium soda, more energetic electron, but not more sodas per quarter, not more electrons. These two problems might seem disconnected, but they shared a common thread. They stubbornly refused to fit into the elegant, continuous, and predictable framework of classical physics. The universe, it seemed, was not quite the smooth, unbroken machine physicists had envisioned. Something fundamental was amiss at the very smallest scales, something that hinted at a deeper, stranger reality that was just beginning to reveal itself. The stage was set for a revolution, a breaking away from the familiar world of billiard balls and continuous waves into the truly astonishing realm of quantum mechanics. Energy in packets. Planck, Einstein, and the birth of the quantum. The year is 1900. Max Planck, a German theoretical physicist, found himself wrestling with the ultraviolet catastrophe, the baffling problem of blackbody radiation that classical physics just couldn't explain. He was a conservative scientist, known for his devotion to classical thermodynamics, and certainly not one looking to dismantle the foundations of physics. Yet, the experimental data was undeniable, and it stubbornly defied all attempts to fit it into the existing framework. Driven by a desire to find a mathematical formula that would accurately describe the observed spectrum of light emitted by hot objects, Planck stumbled upon a radical idea. He proposed that the energy radiated by vibrating atoms inside a hot object could not be emitted continuously, like smoothly flowing water from a tap. Instead, it had to be emitted in discrete, individual packets, or quanta, much like water flowing from a tap only in individual drops. Each packet of energy, he suggested, was proportional to the frequency of the radiation. The higher the frequency, the more energetic each packet. This was a profoundly counterintuitive concept. For centuries, energy had been thought of as a continuous quantity, something that could be divided into infinitely smaller pieces. Planck's idea was like saying you couldn't buy sugar in any arbitrary amount. You could only buy it in fixed-size bags. He introduced a new fundamental constant, now known as Planck's constant, represented as h, which established the exact relationship between the energy of a quantum and its frequency. When Planck plugged this bizarre assumption into his formulas, suddenly, perfectly, the theory matched the experimental data. The ultraviolet catastrophe vanished. The mathematical curve of his formula perfectly traced the observed distribution of radiation. But Planck himself didn't fully believe in the physical reality of these quanta. He initially considered them a mere mathematical trick, a computational artifice to force the equations to work, rather than a genuine description of how nature truly behaves. He spent years trying to find a way to derive his formula without this outrageous assumption, but to no avail. The quanta were here to stay. Einstein's bold leap. The photon. 5 years later, in 1905, a brilliant young patent clerk named Albert Einstein took Planck's seemingly abstract mathematical trick and escalated it into a tangible physical reality. Einstein, famous later for his theory of relativity, was then just beginning his incredible streak of groundbreaking papers, often referred to as his annus mirabilis, or miracle year. While Planck had suggested that atoms emit energy in discrete packets, Einstein proposed something even bolder. That light itself, the very thing thought to be a continuous wave, actually consists of these discrete packets of energy. He called them light quanta, which would later be named photons. This wasn't just a slight adjustment to Planck's idea. It was a revolutionary rethinking of light's fundamental nature. If light consisted of these tiny, indivisible packets, it could perfectly explain the photoelectric effect, the second baffling problem from Chapter 1. Imagine those tiny packets of light, photons, hitting a metal surface, much like individual tiny billiard balls hitting a row of larger billiard balls, the electrons. Let's revisit the tricky observations of the photoelectric effect. Frequency matters. If a single photon doesn't have enough energy, i.e., its frequency isn't high enough, according to Planck's formula, it simply can't knock an electron free, no matter how many other low-energy photons hit the surface. It's like trying to break a locked door with a feather. One feather won't do it. A million feathers won't do it. You need a hammer. Instantaneous ejection. If a photon does have enough energy, high enough frequency, it transfers its energy to an electron in a single instant, like one billiard ball striking another square on. The electron pops off immediately. There's no need for energy to accumulate over time. Electron energy proportional to frequency. Each photon has an energy directly proportional to its frequency. So, a higher frequency photon means a more energetic hit, resulting in a more energetic electron being ejected. Brighter light simply means more photons, so more electrons are ejected, but each individual electron still receives the same amount of energy from its individual photon, assuming the frequency is the same. Einstein's light quanta hypothesis perfectly explained every detail of the photoelectric effect. Yet, even though it was a stunning success, it was so radical that the scientific community initially resisted it. Light was a wave. That was an established fact. How could it also be a particle? Einstein received the Nobel Prize in Physics in 1921, not for relativity, but specifically for his explanation of the photoelectric effect and his recognition of the quantized nature of light. Bohr and the quantized atom. The next major leap came from Danish physicist Niels Bohr in 1913. Building on Planck's and Einstein's ideas, Bohr applied the concept of quantization to atomic structure. At the time, Rutherford's experiments had shown that atoms consisted of a dense, positively charged nucleus with electrons orbiting it, much like planets around a sun. However, classical physics predicted that these orbiting electrons should continuously lose energy and spiral inward, eventually crashing into the nucleus. Atoms, according to classical physics, shouldn't be stable, but clearly they are. Bohr proposed that electrons in an atom could only exist in specific, discrete energy levels or orbits around the nucleus, not just any orbit. Think of these as steps on a ladder. An electron can be on rung 1 or rung 2, but never suspended in between. An electron could jump from one energy level to another, but only by absorbing or emitting a specific, precise quantum of energy. A photon whose energy exactly matched the difference between the two allowed levels. This brilliantly explained why atoms emit and absorb light only at very specific frequencies, producing the characteristic fingerprints of elements when their light is observed through a prism. It was a groundbreaking model that brought stability to the atom and further cemented the idea that energy within matter itself is quantized. The contributions of Planck, Einstein, and Bohr marked the true birth of quantum mechanics. They ripped away the comfortable certainty of the continuous, predictable classical world and bravely stepped into a realm where energy exists in discrete packets, where light could be both a wave and a particle, and where electrons could only occupy certain, allowed, parking spots in an atom. This wasn't just a fine-tuning of existing theories. It was a fundamental shift, revealing that at its most basic level, reality was anything but smooth and continuous. It was chunky, probabilistic, and often utterly bizarre. This unraveling of the atomic world was only the beginning of the quantum wonders. Waves and particles, the great duality. By the early 20th century, the scientific community found itself in a paradoxical position. On one hand, experiments like Thomas Young's classic double-slit experiment, performed in 1801, convincingly proved that light behaved as a wave, displaying interference patterns, characteristic ripples that only waves can produce. On the other hand, Einstein's explanation of the photoelectric effect and Planck's earlier work presented compelling evidence that light also behaved as discrete packets of energy, or particles, which he called photons. How could light be both a wave and a particle? This question, fundamental to quantum mechanics, didn't just present a challenge. it introduced a profound mystery at the very heart of nature. This perplexing idea is known as wave-particle duality. It's not that light sometimes acts like a wave and sometimes like a particle, but that it universally exhibits properties of both, depending on how you choose to observe it. To understand this duality, let's revisit the double-slit experiment. Imagine an opaque screen with two tiny, parallel slits cut into it. Behind this screen, there's a detector or a photographic plate. If you shine a beam of water waves at these two slits, what happens? The waves pass through both openings, and as they emerge on the other side, they create new ripples. These ripples interfere with each other. Where crests meet crests, they reinforce each other, creating a bigger wave. Where crests meet troughs, they cancel out. The result on the measuring screen would be an interference pattern, alternating bands of high and low intensity. This is unmistakably wave-like behavior. Now imagine we're firing a stream of tiny particles, like miniature tennis balls, at the same two slits. If a tennis ball hits the wall, it stops. If it goes through a slit, it continues. If you fire enough tennis balls, they'll pass through one slit or the other and build up two distinct piles on the detector screen, one behind each slit. This is clearly particle-like behavior. Light's peculiar behavior. When physicists perform the double-slit experiment with light, you might expect it to behave like one or the other based on whether you assume it to be a wave or a particle. But it defies simple classification. It behaves like both. If you shine a steady beam of light at the slits, the light creates an interference pattern on the screen, just like water waves do. This confirms light's wave nature. But here's where it gets truly strange. What if we dim the light source so much that only one photon at a time is sent towards the slits? If each photon is a discrete particle, you'd expect them to behave like our miniature tennis balls, each going through either the left slit or the right slit, and eventually building up two distinct piles on the screen. However, when you run this experiment, sending one photon at a time, and let the photons accumulate over a long period, something astonishing happens. An interference pattern still emerges. It's as if each individual photon, somehow, travels through both slits simultaneously and interferes with itself. How can a single, indivisible particle go through two places at once? This is the core perplexity of wave-particle duality. The duality extends to matter. For a while, this bizarre duality was thought to be a property unique to light. But in 1924, a young French physicist named Louis de Broglie dared to propose a truly revolutionary idea. If waves of light could act like particles, then perhaps particles of matter, like electrons, could also act like waves. He boldly suggested that every particle has an associated wavelength, now known as the de Broglie wavelength, inversely proportional to its momentum. The heavier the object or the faster it moves, the shorter its wavelength. For everyday objects, this wavelength is infinitesimally small, making their wave-like properties utterly undetectable. But for tiny, fast-moving particles like electrons, this wavelength is significant. Scientists quickly put de Broglie's hypothesis to the test. In 1927, experiments by Clinton Davison and Lester Germer, and independently by George Paget Thomson, showed that electrons, thought to be quintessential particles, indeed exhibited wave-like behavior, diffracting through crystals just as X-rays, a form of light, would. And yes, electrons also produce an interference pattern in the double-slit experiment, even when sent one at a time. The same bizarre behavior observed with photons also holds true for bits of matter like electrons, and even larger particles like atoms and molecules. Where does the wave go? This leads to an even deeper mystery. If you try to figure out which slit the photon or electron goes through by placing a detector near the slits, the interference pattern disappears. Instead, you get the classic two piles pattern, as if you were firing tennis balls. The act of observation, of measuring which path the particle takes, seems to force it to choose one path, thereby destroying its wave-like nature and its ability to interfere with itself. It's as if the particle knows it's being watched and changes its behavior. This is not some trick of the experiment or a flaw in our instruments. It's a fundamental property of the quantum world. The very act of observing or measuring a quantum system influences its behavior. The wave properties of a quantum entity, like its ability to be in multiple places at once, are exquisitely fragile. Any attempt to pin down its precise location, to act like a particle, causes its wave-like nature to vanish. The implications are profound. Particles don't simply have a definite position and momentum that we somehow manage to disturb when we measure them. Instead, it seems that before we observe them, they exist in a fuzzy, probabilistic state where their wave-like properties dominate. The double-slit experiment, in its simplicity, lays bare the radical departure of quantum mechanics from our everyday intuition and sets the stage for even stranger concepts. How a particle can be in multiple places at once until we look at it. This will be the subject of our next chapter, superposition and the measurement problem. The ghost in the machine, superposition and the act of measurement. In the previous chapter, we saw how particles, like photons and electrons, exhibit an uncanny wave-particle duality, famously demonstrated by their ability to pass through two slits at once and create an interference pattern. This behavior hints at a profoundly counterintuitive notion, that a quantum particle doesn't simply occupy one definite state or position. Instead, it seems to exist in a kind of fluid, indeterminate state until observed. This is the concept of superposition. At its core, superposition means that a quantum system can exist in multiple possible states simultaneously. It's not that we don't know which state it's in. Rather, it is genuinely in a combination of all of them at once. For example, an electron can be spinning both clockwise and counterclockwise at the same time, or an atom can be both excited and unexcited. A quantum particle moving towards a barrier can, in a sense, be in a superposition of going through and bouncing off. To help grasp this, imagine a coin spinning in the air. Before it lands, it's neither definitively heads nor tails. It contains the potential for both outcomes. In an analogy to superposition, you could say it's in a state of heads and tails simultaneously. It's only when it lands, or when you slap your hand down, that it collapses into a single, definite state, either heads or tails. The quantum world takes this idea much further. While our spinning coin is ultimately a classical object whose state is merely unknown to us until it lands, a quantum particle is truly, fundamentally existing in all its potential states at once until an interaction forces it to pick one. The problem of observation. This brings us to one of the most enigmatic aspects of quantum mechanics, the measurement problem. If a particle exists in a superposition of states, what causes it to choose just one? The answer, as the double-slit experiment hinted, seems to be the act of measurement or observation. The moment you interact with a quantum system in a way that allows you to determine its state, whether by shining a light on it, touching it with another particle, or simply putting a detector in its path, its superposition collapses. The system abruptly snaps from being a fuzzy combination of possibilities into a single, definite reality. It's as if the very act of looking forces the universe to make up its mind. This is profoundly unsettling because it implies that reality isn't just there, independently of us. Our interaction with the quantum world seems to play an active, even creative, role in shaping its very properties. What constitutes an observation? Does it require a conscious observer, or just any interaction with the environment that could potentially reveal information? The current understanding leans towards the latter. Any interaction, such as a particle bumping into an air molecule, can cause its superposition to collapse. Schrödinger's cat, a famous thought experiment, to highlight the bizarre implications of superposition and the measurement problem, Austrian physicist Erwin Schrödinger devised a famous thought experiment in 1935. It's not meant to be a real experiment, but rather to expose the absurdity of applying quantum rules to our macroscopic world. Imagine a highly complex, isolated setup within a sealed, opaque steel box. Inside, there's a living cat, a flask of poisonous gas, and a single radioactive atom. This atom has a 50% chance of decaying within 1 hour. If it decays, it triggers a Geiger counter, which in turn causes a hammer to smash the flask, releasing the poison and killing the cat. If the atom doesn't decay, the cat lives. From a quantum perspective, the radioactive atom, until observed, is in a superposition of decayed and undecayed states. Because the fate of the cat is inextricably linked to the state of the atom, it follows that, according to the standard interpretation of quantum mechanics, the poor cat inside the box is in a superposition of dead and alive simultaneously. It is neither and both until we open the box and make an observation. At that exact moment, the superposition collapses, and we find the cat definitively either dead or alive. Schrödinger intended for this thought experiment to be absurd. We never encounter dead-alive cats in our everyday lives. This highlights a fundamental tension. Quantum mechanics describes the subatomic world with incredible accuracy, but its principles seem utterly nonsensical when scaled up to everyday objects. Decoherence, why we don't see dead-alive cats. So, why don't we see everyday objects existing in superpositions? The most accepted explanation for the apparent collapse of superposition, particularly for larger objects like cats, is a phenomenon called decoherence. Decoherence describes how quantum systems lose their quantum properties, like superposition, almost instantly when they interact with their environment. The environment here isn't just you looking at it. It's any interaction with air molecules, stray photons, thermal energy, or even gravitational fields. Every particle in the cat is constantly interacting with vast numbers of other particles. Think of it like a carefully balanced house of cards. A quantum superposition is fragile, easily disturbed. Any slight disturbance from the environment, even just a few particles bumping into the house of cards, will cause it to tumble. What was once a superposition of possibilities becomes a single, definite reality. For a single electron, maintaining a superposition is relatively easy in a controlled lab environment. For a cat, which is made of trillions of atoms constantly bumping into each other and interacting with countless particles in the air, maintaining a superposition is practically impossible. The information about the cat's state quickly leaks into the environment, effectively performing a continuous measurement and forcing the cat into a definite state, either alive or dead. Decoherence doesn't fully answer why superposition exists or what exactly constitutes a measurement, but it does explain why we don't observe superposition in the macroscopic world. It neatly bridges the gap between the weirdness of the quantum realm and the seemingly stable reality we experience. The ghost in the machine, the idea that a quantum particle can exist as a mere potentiality until observed, deeply challenges our intuitive understanding of reality. It forces us to confront the possibility that the universe at its most fundamental level is not a collection of fixed, predetermined objects, but a dynamic, probabilistic web of interactions where our very act of looking helps turn potentiality into reality. This peculiar relationship between observer and observed opens the door to even stranger quantum phenomena, like the instantaneous connection between particles that are light years apart, a phenomenon Einstein famously called spooky action at a distance. Shaky ground, Heisenberg's uncertainty principle. In the peculiar landscape of the quantum world, where particles are also waves and existence itself is a matter of probabilities until observed, one of the most profound and perhaps discomforting principles is Heisenberg's uncertainty principle. Formulated by the German physicist Werner Heisenberg in 1927, this principle states that there are fundamental limits to the precision with which certain pairs of physical properties of a particle, like its position and momentum, can be simultaneously known. This isn't about the limitations of our measuring instruments. It's not that our tools aren't good enough or that we're clumsy scientists. Rather, it's a built-in, intrinsic property of nature itself. The universe, at its most fundamental quantum level, simply doesn't allow for absolute certainty in these paired properties. Let's unpack this with the classic example: position and momentum. Momentum, for our purposes, can be thought of as a particle's mass multiplied by its velocity or speed in a given direction. Imagine you're trying to precisely pinpoint the exact location of an electron. To see it, you might shine a light on it. Light, as we know, consists of photons. When a photon hits the electron, it gives the electron a kick. The more precisely you want to know the electron's position, the shorter the wavelength of light you need to use, e.g., higher frequency photons. But shorter wavelength photons carry more energy and thus deliver a bigger kick to the electron. This kick inevitably changes the electron's momentum in an unpredictable way. Conversely, if you want to precisely determine the electron's momentum, you'd need to let it travel undisturbed for a period to accurately gauge its speed and direction. But in doing so, you lose information about its exact position at any given moment. It's a bit like trying to perfectly locate and perfectly photograph a tiny, incredibly delicate moth by throwing paint at it. The paint will tell you where it was, but the act of throwing the paint inevitably splashes the moth, altering its flight path, so you no longer know its exact momentum. And the more precisely you want to locate it, smaller paint splatters, the harder you have to throw, ensuring an even greater disturbance. The intrinsic nature of uncertainty. Crucially, the uncertainty principle is not about the disturbance caused by observation, though that analogy helps explain why it feels so counterintuitive. More fundamentally, it implies that before any measurement, a quantum particle does not possess a perfectly defined position and a perfectly defined momentum simultaneously. It's not that these properties exist but are hidden from us. It's that the quantum state itself is described by a probabilistic distribution for both, and trying to narrow down one necessarily broadens the other. This means that the quantum world is intrinsically fuzzy. If you define a particle's position with absolute pinpoint accuracy, its momentum becomes completely indeterminate, like a blur on a photograph. And if you perfectly define its momentum, its position spreads out across the universe. Other pairs of properties also exhibit this uncertainty relationship, such as energy and time. The more precisely you measure the energy of a system, the longer you need to take that measurement, and vice versa. This allows for what are called virtual particles to pop into and out of existence from seemingly empty space for incredibly tiny durations, borrowing energy from the vacuum for that brief moment. This is a profound implication, as it means even empty space is teeming with activity. The uncertainty principle and our worldview. The uncertainty principle directly challenges the deterministic worldview inherited from classical mechanics. Newton's physics suggested that if you knew the initial conditions, you could predict the future with absolute certainty. Heisenberg's principle says, not so fast. At the quantum level, you can never even know the initial conditions with absolute certainty because of this inherent fuzziness. This means that true, fundamental randomness exists in the universe. God does not play dice, as Einstein famously declared, expressing his discontent with this probabilistic nature of quantum mechanics. But the quantum dice, it turns out, are indeed thrown. One of the most powerful and visible manifestations of the uncertainty principle is in the very structure of atoms. According to classical physics, electrons orbiting a nucleus should spiral inward and crash. But they don't. The uncertainty principle explains why. If electrons were to crash into the nucleus, their position would become perfectly known at the nucleus, which would mean their momentum would have to be infinitely uncertain. This infinite uncertainty in momentum implies an incredibly high kinetic energy, which would immediately kick the electron out of the nucleus. So the electron can't just sit perfectly still at the nucleus. Instead, it settles into an orbit where there's a balance, a cloud-like probability distribution of where it might be, which is often referred to as an electron cloud or orbital. The electron's position becomes inherently uncertain, reflecting its wave-like nature. The uncertainty principle is not just a theoretical concept. Its implications are crucial for understanding everything from the stability of atoms to how microscopes work. It demonstrates that our attempts to categorize the universe definitively run up against an intrinsic quantum reality. The more we try to grasp one aspect of a particle, the slipperier another becomes, forcing us to acknowledge that reality at its smallest scales is inherently probabilistic, a shaky ground on which our seemingly solid world is built. This fundamental unpredictability sets the stage for an even more mind-bending quantum phenomenon, the mysterious, instantaneous connection between distant particles that we call entanglement. Spooky action at a distance. The riddle of entanglement. If superposition and uncertainty challenge our very notions of what exists and what can be known, then quantum entanglement strikes at the heart of how we understand connections and relationships in the universe. Of all the bizarre phenomena in quantum mechanics, entanglement is perhaps the most mind-bending, leading Albert Einstein to famously dismiss it as spooky action at a distance. So, what is entanglement? Imagine two particles that are intrinsically linked, no matter how far apart they are. They are born together or interact in such a way that their fates become intertwined. When you measure a property of one entangled particle, such as its spin or polarization, you instantly know the corresponding property of the other particle, even if the second particle is light years away. This happens faster than the speed of light, defying our classical understanding of information transfer. Let's use an analogy, though like all quantum analogies, it has its limitations. Imagine you have two identical boxes, and inside each box is a glove, one left-handed, one right-handed. You put them into two separate boxes, and without peeking, you give one box to a friend who then travels to the moon, while you keep the other on Earth. When your friend opens their box on the moon and finds a left-handed glove, you instantly know that the glove in your box on Earth is right-handed. There's no mystery here. The gloves were predetermined. But quantum entanglement is profoundly different. In the quantum world, the particles don't have a determined property until one of them is measured. It's as if neither glove was left-handed or right-handed until your friend opened their box. The act of opening your friend's box and finding a left-handed glove causes your glove to instantly become right-handed, no matter how far away it is, and this decision happens simultaneously for both. This is the core of the spookiness. It's not just that we don't know the state of the particles beforehand, it's that the particles exist in a combined, indeterminate state, a superposition of correlated possibilities until one is measured. The measurement on the first particle instantly collapses the superposition of the entire entangled pair, fixing the states of both particles. This appears to violate two deeply ingrained classical principles: locality, the idea that an object can only be influenced by its immediate surroundings; realism, the idea that physical properties exist independently of being measured. Einstein's challenge. The EPR paradox. Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, devised a thought experiment in 1935, now known as the EPR paradox, to argue that quantum mechanics must be incomplete. They conceded that entanglement seemed to predict spooky action at a distance. And because nothing could travel faster than light, according to Einstein's own theory of relativity, this implied that the particles must have already had their properties predetermined from the moment they were created. They called these hidden variables. In their view, entanglement wasn't spooky action, it was simply ignorance. The particles knew what properties they would display all along, but quantum mechanics just didn't tell us. Niels Bohr, another giant of quantum physics, famously debated with Einstein over this. Bohr argued that quantum mechanics was complete and that the properties of entangled particles truly did not exist until measured. He emphasized that the entangled particles should be thought of as a single, indivisible system, and the act of measurement on one was a measurement on the whole system, regardless of distance. The debate raged for decades, largely philosophical, because there was no way to experimentally test whether hidden variables actually existed. John Bell and experimental proof. In 1964, a brilliant physicist named John Bell entered the fray. He devised a mathematical theorem, later known as Bell's theorem, which showed that if Einstein's hidden variables theory were true, there would be certain limits to the correlations that could be observed between entangled particles. If quantum mechanics was true, and there were no hidden variables and truly spooky action, then these correlations could be stronger. Bell's theorem essentially turned a philosophical debate into an experiment. Several physicists took up the challenge, most notably Elaine Aspect in 1982, and many others since. These experiments involved creating entangled pairs of particles, usually photons, and sending them in opposite directions to separate detectors. The detectors then measured a specific property of the particles, often their polarization, the direction their electric field oscillates. The results were astonishing and consistent. The correlations observed between the entangled particles violated Bell's inequalities. This means that the correlations were stronger than could be explained by any local hidden variable theory. The particles indeed seemed to be in an indeterminate state until measured, and their properties became correlated instantaneously, faster than light, across vast distances. It doesn't mean that information can be sent faster than light. You can't use entanglement to send a message to the moon. You can't control what outcome your distant friend gets when they open their box. You only know, once they tell you what they saw at light speed or slower, that your result was perfectly correlated. But it does mean that in the quantum world, our notions of distinct, separate objects break down. Entangled particles truly behave as a single, non-local entity. The strange reality of entanglement. Entanglement shows that the universe is far more interconnected than we ever imagined. It's a quantum leap from the classical idea of separate, independent objects interacting only through forces. Objects in the quantum world can be so deeply entwined that measuring one instantly influences the other, regardless of the distances between them. This phenomenon is not just a theoretical oddity, it's being harnessed. Entanglement is the foundational principle for burgeoning fields like quantum computing, where linked quantum bits, qubits, allow for vastly more complex calculations than classical computers. It's also vital for quantum cryptography, enabling perfectly secure communication channels. The spooky action at a distance that so troubled Einstein now stands as one of the most rigorously tested and experimentally verified phenomena in physics. It pushes us to redefine our understanding of cause and effect, locality, and what it truly means for something to be real in a universe governed by quantum rules. It reminds us that at its smallest scales, reality is far stranger and more wondrously interconnected than our everyday intuition can easily grasp. The spin of reality. Intrinsic properties of the quantum world. As we've journeyed deeper into the quantum realm, we've encountered particles that are also waves, that can be in multiple places at once, and that are spookily linked across vast distances. Now, let's explore another intrinsic property of quantum particles that has no direct classical counterpart, yet is vital for understanding how the universe works: quantum spin. In our everyday world, when we talk about spin, we usually think of an object rotating, like a spinning top or the Earth rotating on its axis. This classical spin involves actual physical rotation and depends on the object's size and mass distribution. Quantum spin, however, is very different. It's an inherent or intrinsic property of a particle, much like its mass or electrical charge. It's a bit misleading to call it spin in the classical sense, because quantum particles are often considered point-like. They have no physical extent or structure to actually rotate. Imagine an electron. It is generally considered a fundamental, point-like particle, yet it possesses spin. This quantum spin is not a physical rotation, but rather an intrinsic form of angular momentum. It's a fundamental quantum number that dictates how a particle behaves in a magnetic field, how it interacts with other particles, and forms the basis for many quantum phenomena. Spin up or spin down. For electrons and other fundamental particles like quarks and neutrinos, their quantum spin can only take on certain discrete values. For an electron, it can only be spin up or spin down when measured along any given axis. It's like a tiny, fundamental magnet that can only point in one of two directions in relation to an external magnetic field. Just like with superposition, an electron that hasn't been measured along a certain axis might exist in a superposition of both spin up and spin down simultaneously. The act of measuring its spin forces it to choose one of these definite states. The Stern-Gerlach experiment. The existence of quantum spin was elegantly demonstrated by the Stern-Gerlach experiment, performed in 1922 by Otto Stern and Walther Gerlach. Though they didn't know it was spin at the time, they were trying to measure the magnetic properties of silver atoms. Their results provided strong evidence for the quantization of angular momentum. Imagine you have a beam of silver atoms. Each atom vaguely acts like a tiny magnet due to its electrons. If you send these atoms through a spatially varying magnetic field, a field that is stronger at one end than the other, classical physics would predict that the atoms, with their randomly oriented magnetic moments, would be deflected by varying amounts, creating a continuous smear of deflected atoms on a detector screen. If the field is perfectly uniform, there would be no deflection at all. A non-uniform field would sort them out according to their magnetic strength and orientation. However, when Stern and Gerlach performed the experiment, they observed something remarkable. The continuous smear wasn't there. Instead, the beam of silver atoms split into two discrete beams. This showed that the atoms weren't randomly oriented. Their magnetic moments, and thus their intrinsic spin, could only take on a specific, quantized set of values. Spin up or spin down relative to the orientation of the magnetic field. It was like magic. Instead of a smooth distribution, you got two distinct lines, signifying only two allowed settings for the spin. This was a profound result. It was direct experimental evidence that a fundamental property of matter, its intrinsic angular momentum, spin, was quantized, just like energy levels in an atom. It wasn't a continuous dial, but a switch with only two positions. The Pauli exclusion principle. The concept of quantum spin becomes even more powerful when combined with another fundamental rule governing particles, the Pauli exclusion principle, formulated by Wolfgang Pauli in 1925. This principle states that no two identical particles with half-integer spin, like electrons, protons, and neutrons, which are called fermions, can occupy the same quantum state simultaneously in an atom. Think of it like this. If electrons are like people trying to sit in chairs, energy levels orbitals, in a very specific room, an atom, the Pauli exclusion principle is the rule that says each chair can only hold two people, and only if they are spinning in opposite directions, one spin up, one spin down. Without this principle, all electrons would simply pile into the lowest energy level, and atoms wouldn't have their complex, stable structures. There would be no chemistry, no diverse elements, no life. The Pauli exclusion principle, underpinned by quantum spin, is directly responsible for the vast diversity of the chemical elements and their unique properties, which, in turn, allows for all the complex molecules and reactions that make up our world, and indeed ourselves. The role of spin in the universe. Quantum spin, despite its abstract nature, is immensely important. Atomic structure and chemistry. As mentioned, it dictates how electrons fill orbitals, giving rise to the periodic table and the very possibility of chemical reactions. Magnetism. The magnetic properties of materials, from the permanent magnets on your fridge to the workings of an MRI machine, are fundamentally rooted in the alignment of electron spins. Quantum computing. Spin is a key property often used to define a quantum bit, or qubit, where spin up might represent a 1 and spin down a 0, enabling superposition and entanglement for computation. Particle physics. Spin helps classify fundamental particles and understand their interactions in the Standard Model. So, while spin might conjure images of whirling objects, in the quantum realm, it's a deeply intrinsic, abstract property, quantized and fundamentally tied to the very identity and behavior of particles. It underscores how the quantum world operates on a set of rules profoundly different from our macroscopic experience. Yet these rules are the bedrock upon which our entire, rich universe is built. And that bedrock has a few more surprises in store, including particles seemingly passing through solid barriers, which is the subject of our next chapter. Through the walls. Quantum tunneling and its surprising presence. Imagine tossing a ball at a wall. Unless you throw it hard enough to break through, or there's a hole in the wall, the ball will always bounce back. This is intuitive, based on our everyday experience and the classical laws of physics. If an object doesn't have enough energy to overcome a barrier, it simply cannot pass through it. This is true for tennis balls, cars, and even individual atoms in large collections. But in the quantum realm, this common-sense rule doesn't always apply. Quantum particles, with their intrinsic wave-like nature, can sometimes pass through energy barriers that they classically shouldn't be able to overcome. This phenomenon is called quantum tunneling. It's as if our tennis ball, instead of bouncing off the wall, occasionally slips right through it and appears on the other side, even if it didn't have nearly enough energy to get over or through it by conventional means. This is not science fiction. It's a fundamental aspect of reality at the subatomic level, and it's a direct consequence of a particle's wave properties and the uncertainty principle. How does tunneling work? Recall that in quantum mechanics, a particle isn't just a tiny, localized point. It's also described by a wave function that represents the probability of finding the particle at any given location. When a quantum particle encounters an energy barrier, a region of higher potential energy, its wave function doesn't abruptly drop to 0 at the barrier's edge. Instead, it decays exponentially through the barrier. This means there's a small, but non-zero, probability of finding the particle on the other side of the barrier, even if it doesn't possess the classical energy required to surmount it. Although the probability of tunneling decreases rapidly with the thickness and height of the barrier, for incredibly tiny particles negotiating incredibly tiny barriers, it happens routinely. Think of it this way: the particle briefly borrows energy to get through the barrier, without violating the conservation of energy in the long run. Due to the energy-time uncertainty principle, a particle can briefly exist with an energy that seems to violate conservation laws, as long as it's for an extremely short period. If it tunnels, it pays back the borrowed energy, where quantum tunneling pops up. Quantum tunneling might sound like an esoteric concept confined to theoretical physics, but it's a crucial phenomenon that underpins many natural processes and technologies. Nuclear fusion in the sun. This is perhaps the most awe-inspiring example. The core of our sun and other stars is incredibly hot, but not hot enough for hydrogen nuclei to overcome their mutual electrostatic repulsion entirely and fuse into helium according to classical physics. If not for quantum tunneling, the sun wouldn't burn, and life as we know it wouldn't exist. Protons in the sun's core tunnel through the electrostatic barrier, allowing fusion reactions to occur, releasing the enormous energy that powers the star. Radioactive decay. Many heavy, unstable atomic nuclei undergo alpha decay, where they emit an alpha particle, a helium nucleus. Classically, the alpha particle is held within the nucleus by a strong nuclear force, but it also has to overcome an electrostatic repulsion from the rest of the nucleus to escape. It doesn't have enough energy to classically climb over this barrier. Instead, it quantum tunnels its way out, allowing the nucleus to decay. DNA mutations. Quantum tunneling can even play a role in biological processes. For instance, in DNA replication, protons, hydrogen nuclei, can tunnel between bases, causing mutations. While the probability is small, it highlights the quantum nature of even biological information. Scanning tunneling microscopes, SDM. This is a remarkable technological application. An SDM uses a superfine, electrically conducting tip brought incredibly close to a conducting surface, within a few atomic diameters. If a voltage is applied, electrons can quantum tunnel from the tip to the surface, or vice versa, creating a tiny, tunneling current. The current is exquisitely sensitive to the distance between the tip and the surface. By scanning the tip across the surface and maintaining a constant tunneling current, by moving the tip up and down, the SDM can produce incredibly detailed, atom-by-atom topographical maps of surfaces. It allows us to see individual atoms, semiconductors, and electronics. Quantum tunneling is exploited in many modern electronic devices. For example, in flash memory, used in USB drives and solid-state drives, electrons tunnel through a thin insulating layer to get trapped, storing information. Diodes and transistors also utilize tunneling effects to control electron flow in circuits. Quantum tunneling is a powerful reminder that at the quantum scale, particles behave in ways that seem utterly magical from our macroscopic perspective. The universe is not bound by the limitations we perceive based on our everyday experiences. Instead, it operates on a deeper level where probabilities, wave functions, and the fundamental fuzziness of reality allow for phenomena like tunneling, a silent, invisible process that is nevertheless essential for the burning of stars, the decay of radioactive elements, and the functionality of the very devices we use every day. It's another piece of the quantum puzzle that keeps surprising us, and which will continue to do so as we delve into the fundamental building blocks of the universe in our next chapter. Building blocks and their forces. From quarks to the Standard Model, we've explored the bizarre behaviors of individual quantum particles, their duality, superposition, uncertainty, entanglement, and even their ability to tunnel through barriers. But what are these particles, and what forces govern their interactions? The answer lies in the Standard Model of particle physics, a triumph of 20th century science that combines quantum mechanics with special relativity to describe the fundamental building blocks of matter and the forces through which they interact. Imagine trying to break down all the matter in the universe into its smallest, indivisible components. For centuries, atoms were thought to be the ultimate, fundamental particles. The word atom itself comes from the Greek for uncuttable. Then came electrons, protons, and neutrons. For a while, these three were considered the new fundamental particles. But the proton and neutron, it turns out, are not so fundamental after all. The rise of quarks. Physicists in the 1960s, using powerful particle accelerators, began smashing protons and neutrons together at extremely high energies. They observed that these particles seemed to have internal structures, and when hit hard enough, they would reveal even smaller, more fundamental constituents. This led to the proposal of quarks by Murray Gell-Mann and George Zweig in 1964. There are 6 flavors of quarks: up, down, charm, strange, top, and bottom. Protons and neutrons are made up of combinations of these quarks. A proton, for example, consists of 2 up quarks and 1 down quark ood, while a neutron is 1 up quark and 2 down quarks ud. We've never observed a quark existing in isolation. They are always found bound together in composite particles like protons and neutrons. This phenomenon is called confinement. Alongside quarks, the other family of fundamental matter particles is leptons. The most famous lepton is the electron, which is truly fundamental, as far as we know right now. Other leptons include the muon, tau, and 3 types of neutrinos: electron neutrino, muon neutrino, and tau neutrino, incredibly light, elusive particles that interact very weakly with other matter. These quarks and leptons make up the matter particles of the Standard Model. They have specific quantum numbers, like spin, charge, flavor, that define their identity and behavior, the 4 fundamental forces, and their carriers. But just having building blocks isn't enough. They need to interact. The Standard Model also describes the fundamental forces that govern these interactions: the strong nuclear force. This is the most powerful force in the universe, active only over incredibly short distances, within the nucleus of an atom. It's responsible for binding quarks together to form protons and neutrons, and also for holding atomic nuclei together, overcoming the electromagnetic repulsion between positively charged protons. The particles that carry this force are called gluons. Think of gluons as cosmic glue, holding quarks firmly together. The weak nuclear force. This force is responsible for radioactive decay, including processes that cause protons to turn into neutrons and vice versa. It's crucial for processes like nuclear fusion in the sun and certain types of radioactivity. It's carried by 3 particles known as the W and Z bosons. Unlike gluons, these force carriers are massive, which is why the weak force has an even shorter range than the strong force. The electromagnetic force. This familiar force governs all interactions between electrically charged particles. It's responsible for everything from light and radio waves to chemical bonds, electricity, and magnetism. The force carrier for electromagnetism is the photon, the quantum of light we encountered earlier. When 2 charged particles interact, they exchange photons. Gravity. Perhaps surprisingly, gravity is not part of the Standard Model. While we experience gravity constantly as the force that keeps our feet on the ground and planets in orbit, its quantum description remains elusive. Scientists hypothesize that gravity is carried by a particle called the graviton, but this particle has never been detected, and a consistent theory of quantum gravity that unifies general relativity with the Standard Model remains one of the holy grails of modern physics. The Higgs boson, giving mass to particles, a crucial piece of the Standard Model puzzle, was confirmed relatively recently. For particles to have mass, there needed to be a mechanism that endowed them with it. This led to the theoretical prediction of the Higgs field and its associated particle, the Higgs boson. Imagine the universe permeated by an invisible field. As particles move through this field, they interact with it, and this interaction gives them mass. The more they drag through the Higgs field, the more massive they are. The Higgs boson is like an excitation or a ripple in this field. Its discovery at the Large Hadron Collider, LHC, in 2012 was a monumental achievement in particle physics. Quantum field theory, the underlying framework. The Standard Model is built on the framework of quantum field theory, QFT. In QFT, particles are not seen as tiny billiard balls. Instead, the universe is thought to be made up of fundamental fields that permeate all of space. Particles are essentially excited states or localized ripples within these fields. So, an electron isn't a tiny ball. It's an excitation in the electron field. A photon is an excitation in the electromagnetic field. When particles interact, it's actually their corresponding fields interacting by exchanging the force-carrying particles. This unified framework beautifully explains how particles are created and annihilated, and how they interact through forces. The Standard Model is incredibly successful. It has accurately predicted the existence of many particles before they were experimentally discovered, and its predictions have been verified with astonishing precision in countless experiments. It's the most complete and accurate description we have of matter and 3 of the 4 fundamental forces. However, it's not a complete theory of everything. It doesn't include gravity, it doesn't explain the existence of dark matter or dark energy, and it leaves questions about neutrino masses unanswered. Despite its limitations, the Standard Model stands as a monumental achievement, a testament to the power of quantum mechanics to describe the universe at its most fundamental level, revealing a hidden world of quarks, leptons, and force carriers. These are the elusive, ephemeral foundations upon which all of observable reality is built, and understanding them has opened up incredible technological possibilities, which we'll explore next. Quantum leaps in technology. Everyday wonders. Quantum mechanics might seem abstract, a realm of thought experiments, invisible particles, and spooky connections. But the truth is, the insights gained from understanding the quantum world haven't just satisfied scientific curiosity, they have fundamentally reshaped our world. Many of the technologies we now take for granted, devices found in nearly every home and hospital, are direct beneficiaries of our ability to harness the bizarre rules of the very small. We literally live in a quantum age. Lasers, coherent light unleashed. One of the most recognizable quantum technologies is the laser. The word laser is an acronym for light amplification by stimulated emission of radiation. Its principles were first laid out by Albert Einstein in 1917 through his work on stimulated emission, a purely quantum process. Here's the quantum magic. In materials like ruby or certain gases, electrons normally reside in specific energy levels. If an electron is in a higher energy level, it can spontaneously drop to a lower level, emitting a photon. This is called spontaneous emission. But Einstein theorized that if a photon with the precise energy difference between 2 levels hits an electron already in that higher energy level, it can stimulate the electron to drop to the lower level and emit another photon that is identical to the first one's same direction, same energy, same phase. This is stimulated emission. A laser works by creating a population inversion, more electrons in a higher energy state than a lower one, and then using mirrors, a resonant cavity, to bounce these, stimulating photons back and forth. Each pass amplifies the light, creating a highly concentrated beam of coherent, monochromatic light. Where do we see lasers? Everywhere. CD and DVD players / Blu-ray. The tiny beams red pits and lands on the disc surfaces. Fiber optics. Lasers transmit vast amounts of data at incredible speeds over long distances, forming the backbone of the internet. Barcode scanners. In retail stores, they quickly read product information. Medical procedures, precision surgery, e.g., eye surgery, dermatology, dental work, and even tattoo removal. Industrial applications. Cutting and welding metals, drilling precision holes. Printers. Laser printers use a laser to draw images onto a drum. Transistors and semiconductors, the digital revolution. Perhaps the most impactful application of quantum mechanics is in the development of semiconductors, which form the basis of transistors, diodes, and ultimately, all modern electronics. The very device you might be reading this on your computer, smartphone, or tablet owes its existence to quantum mechanics. Classical physics couldn't explain why certain materials like silicon and germanium behave as semiconductors, sometimes conducting electricity, sometimes not. Quantum mechanics, specifically the principles of band theory, provided the answer. In solids, electrons are not confined to discrete energy levels like in isolated atoms. Instead, their energy levels broaden into bands. For a material to conduct electricity, there must be available electrons in a conduction band that can move freely. Semiconductors have a band gap, a small energy difference between their valence band, where electrons are normally tightly bound, and their conduction band. By doping these materials with impurities, physicists can create a precise number of mobile electrons, N-type semiconductor, or holes, P-type semiconductor, which act like positive charge carriers. The transistor, invented in 1947 at Bell Labs by John Bardeen, Walter Brattain, and William Shockley, revolutionized electronics. It's a tiny semiconductor device that can amplify electronic signals or act as a switch, turning current on and off. The precise control of electron flow within the transistor is entirely a quantum phenomenon, relying on the careful manipulation of electron energy bands and the small energy required for electrons to jump across the band gap. The ability to miniaturize transistors and integrate billions of them onto a single silicon chip, the integrated circuit, is what powers all our digital devices, enabling the digital age. Magnetic resonance imaging, MRI. Seeing inside the body. MRI is a non-invasive medical imaging technique that provides detailed images of organs, soft tissues, bone, and virtually all other internal body structures. Unlike X-rays, it does not use ionizing radiation, making it very safe. Its fundamental principles lie in quantum mechanics, specifically the quantum spin of atomic nuclei. Many atomic nuclei, particularly hydrogen nuclei, protons, possess a property called nuclear spin, similar to the electron spin we discussed earlier. When placed in a strong external magnetic field, these tiny nuclear magnets tend to align either with or against the field, creating a very small energy difference between these two spin states. An MRI machine works by placing a patient inside a powerful magnetic field, which aligns the spins of hydrogen protons, abundant in water, thus abundant in body tissues, sending a burst of radio waves, a specific quantum of energy. These radio waves cause some of the aligned protons to temporarily flip their spin state, absorbing energy, turning off the radio wave pulse. The protons then relax or return to their original alignment, releasing the absorbed energy as faint radio signals. Measuring these signals. Different tissues, with different water content and chemical environments, relax at different rates, producing distinct signals. A computer then translates these signals into detailed cross-sectional images of the body. The precise energy required to flip the nuclear spins and the way they relax is a purely quantum phenomenon. MRI allows doctors to visualize tumors, detect brain abnormalities, assess heart damage, and examine joint injuries, all without surgery or harmful radiation. Atomic clocks. The ultimate timekeepers. Atomic clocks, which measure time by monitoring the precise frequencies of electromagnetic radiation emitted or absorbed by atoms, are the most accurate timekeeping devices ever invented. Their accuracy is based on the incredibly stable and well-defined quantum transitions between electron energy levels within specific atoms, like cesium-133, the basis for the international definition of the second. When an electron jumps from one energy level to another, it emits or absorbs a photon with a very specific, unchanging frequency. Atomic clocks count these perfectly regular ticks, the oscillations of these transition frequencies. These clocks are so precise that they lose less than a second over millions of years. Atomic clocks are not just scientific curiosities, they are foundational for global technologies. GPS, Global Positioning System. Highly accurate atomic clocks are on board each GPS satellite. Without their precise timing, your GPS device wouldn't be able to calculate your position accurately. Telecommunications. They synchronize communication networks worldwide. Internet. The timing of all internet transactions relies on atomic clocks. These are just a few examples. From superconductors, no electrical resistance at low temperatures, thanks to quantum effects, to quantum dot displays for vivid TV screens. Quantum mechanics has moved beyond the lab to become an indispensable foundation for the technological wonders of our modern world. And the journey is far from over. In the next chapter, we'll delve into the cutting edge, exploring how physicists are now directly exploiting the very weirdness of quantum mechanics to build technologies that were once considered science fiction. Quantum computing and cryptography, the quantum frontier. Computing, cryptography, and beyond. If the previous chapter showcased how quantum mechanics silently underpins much of our modern technology, this chapter will explore the active frontier, where scientists are intentionally harnessing the most counterintuitive aspects of quantum mechanics, like superposition and entanglement, to build technologies that promise to revolutionize computing, communication, and even our understanding of the universe. This is the realm of quantum computing, quantum cryptography, and other emerging quantum technologies. Quantum computing, a leap beyond bits. Our everyday computers, from smartphones to supercomputers, operate using bits. A bit is a binary digit, representing either a 0 or a 1. All calculations, data storage, and information processing are ultimately broken down into sequences of zeros and ones. This classical approach has served us incredibly well, driving the digital age. However, certain computational problems are so complex that even the most powerful classical supercomputers would take billions of years to solve, far longer than the age of the universe. These include problems in drug discovery, materials science, cryptography, and artificial intelligence. This is where quantum computing steps in. Quantum computers use qubits, quantum bits, instead of classical bits. A qubit, thanks to the principle of superposition, can represent not just a 0 or a 1, but both 0 and 1 simultaneously. Imagine holding a spinning coin that is both heads and tails until it lands. A single qubit does this, and as you add more qubits, the processing power explodes exponentially. 2 qubits can represent 4 states at once, 3 qubits 8 states, and so on. A quantum computer with just a few dozen qubits can potentially represent more information than all the bits in all the classical computers on Earth combined. But the real power of quantum computing comes from entanglement. When qubits are entangled, their fates are intertwined. A measurement on one instantly influences the others, no matter how far apart they are. This allows for complex, multivariable calculations to be performed simultaneously across many entangled qubits, leading to phenomena like quantum parallelism, where a quantum computer can explore many possible solutions to a problem at the same time. While still in its infancy, quantum computing holds immense promise for materials science, designing new materials with tailored properties, e.g., superconductors, advanced batteries, drug discovery, simulating complex molecular interactions for faster and more accurate drug development, financial modeling, optimizing investment portfolios and predicting market trends, artificial intelligence, enhancing machine learning algorithms for pattern recognition and optimization, cryptography, potentially breaking current encryption methods, but also creating unbreakable ones. Developing a stable quantum computer is incredibly challenging, as qubits are extremely fragile and susceptible to decoherence, losing their quantum properties due to interaction with the environment. They often need to be kept at temperatures colder than deep space in highly isolated environments. Despite these hurdles, major tech companies and research institutions are making rapid progress, demonstrating quantum supremacy, solving a problem demonstrably faster than any classical computer on specific tasks. Quantum cryptography, unbreakable communication. In an age where digital security is paramount, quantum mechanics offers a revolutionary solution. Quantum cryptography, specifically quantum key distribution, QKD. This technology leverages the uncertainty principle and the fragile nature of quantum states to create communication channels that are fundamentally unhackable. Here's the basic idea. Imagine two people, Alice and Bob, want to share a secret encryption key. In QKD, Alice encodes the key into the quantum states of individual photons, e.g., their polarization, which can be thought of as a quantum 0 or 1. She then sends these photons to Bob. The magic happens if an eavesdropper, Eve, tries to intercept the photons and read their quantum states. Due to the uncertainty principle, the act of measuring a quantum state inevitably disturbs it. So, if Eve tries to measure the polarization of Alice's photons, she will inevitably change their state. This change will be detectable by Alice and Bob when they later compare a portion of their key. If they detect too many errors or disturbances, they know someone has been eavesdropping, and they can discard the compromised key and try again. This provides an unprecedented level of security. It's not just computationally hard for an eavesdropper, It's physically impossible for them to intercept the key without being detected. This is a level of security that classical cryptography cannot offer. Quantum cryptography systems are already being used in limited applications for ultra-secure communications. Beyond computing and cryptography, quantum mechanics is also driving innovation in other exciting areas. Quantum sensors. Ultrasensitive sensors that can detect tiny changes in magnetic fields, gravity, or temperature, with applications in medical diagnostics, navigation, and fundamental physics research. Imagine a quantum magnetic resonance measurement at the single molecule level. Quantum metrology, using quantum phenomena to make incredibly precise measurements. Atomic clocks are an early example, but the field extends to measuring fundamental constants and calibrating scientific instruments with unprecedented accuracy. Quantum imaging, developing new types of cameras and imaging techniques that can see things beyond the capabilities of classical optics, for example, imaging in low light or through scattering media. Quantum simulation, building small, controllable quantum systems to simulate the behavior of other, more complex quantum systems, e.g., in materials science or chemistry, that are too difficult to analyze classically. The quantum frontier is a testament to humanity's enduring curiosity and ingenuity. By delving into the deepest, strangest layers of reality, we are not only unraveling the universe's most guarded secrets, but also constructing tools that promise to reshape our future in ways we can only begin to imagine. The journey into the quantum world is far from over. In fact, we're just beginning to learn its language. This leads us to the biggest question: what does it all mean for our understanding of reality? We will explore this profound question in our final chapter. What does it all mean? Interpretations and the grand mystery. We have journeyed through the quantum realm, from the discrete packets of energy that heralded its birth to the mind-bending concepts of wave-particle duality, superposition, uncertainty, and entanglement. We've seen how these abstract principles are not confined to the pages of textbooks, but underpin the very stability of atoms and power the technologies that define our modern world. But despite its unparalleled success in predicting experimental outcomes and building revolutionary devices, quantum mechanics leaves us with a profound, lingering question. What does it all mean? Unlike classical physics, which described a seemingly objective reality that exists independently of our observation, quantum mechanics forces us to confront the role of the observer and the probabilistic nature of existence at its most fundamental level. The equations of quantum mechanics tell us what will happen when we measure something, the probabilities of different outcomes. But they don't fully explain why it happens or what reality is doing when we're not looking. This has led to various attempts to interpret the theory, each offering a different philosophical lens through which to view the quantum universe. The problem of interpretation. The core of the interpretive challenge lies in the measurement problem. If a quantum particle exists in a superposition of states before measurement, what precisely causes this superposition to collapse into a single, definite outcome? Is it the act of observation by a conscious mind? Is it any irreversible interaction with the environment, decoherence? Or is there something else entirely going on? There is no single, universally agreed-upon answer. Let's briefly look at some of the major interpretations. The Copenhagen interpretation. This is the oldest and arguably most widely accepted interpretation, championed by Niels Bohr and Werner Heisenberg. Core idea. It states that quantum systems exist in a superposition of states until they are measured. The act of measurement itself causes the superposition to collapse into a single, definite outcome. Shut up and calculate, a famous phrase often attributed to adherents of this interpretation, reflecting an agnostic stance on what is really happening. The focus is on the predictive power of the theory and its experimental validation, rather than trying to peek behind the curtain at an unknowable reality before measurement. Implications. It implies a fundamental limit to our knowledge and the inherent probabilistic nature of reality. The properties of a quantum system are not fixed until they are observed. The many worlds interpretation, MWI. Proposed by Hugh Everett III in 1957. Core idea: there is no collapse of the wave function. Instead, every time a quantum measurement is made, the universe splits into multiple parallel universes, one for each possible outcome of the measurement. In one universe, Schrödinger's cat is alive. In another, it's dead. All possibilities are realized in different branches of an ever-expanding multiverse. Implications: it preserves determinism. The wave function always evolves predictably, but at the cost of an infinite number of parallel universes. We only experience one branch. While intriguing, it's difficult to experimentally prove or disprove. De Broglie-Bohm theory, pilot wave theory, proposed by Louis de Broglie and later revived by David Bohm. Core idea: this interpretation posits the existence of hidden variables, where particles do have definite positions and momenta at all times, guided by a pilot wave, the wave function. There is no collapse. The particles simply follow definite trajectories dictated by this wave. Implications: it offers a deterministic view of reality, eliminating the need for wave function collapse. However, it requires these pilot waves to be non-local, instantaneously influencing distant particles, which means it embraces the spooky action at a distance directly, rather than explaining it away. It's also often criticized for being counterintuitive in other ways. These are just a few of the many interpretations, each with its defenders and detractors. Others include quantum Darwinism, relational quantum mechanics, and objective collapse theories. What unites them is their attempt to provide a coherent narrative for the quantum mechanical equations we know work so incredibly well. The grand mystery endures. The ongoing debate over interpretations highlights the fact that quantum mechanics is not just a scientific theory. It's a profound philosophical challenge. It doesn't just tell us how the universe works, it forces us to reconsider the very nature of reality, observation, and even consciousness. Despite the philosophical disagreements, all physicists agree on the incredible accuracy and predictive power of quantum mechanics. It is, without a doubt, the most successful scientific theory ever devised, forming the bedrock of nearly all modern physics and technology. It has passed every experimental test thrown at it with stunning precision. So, what should you take away from this journey into the quantum world? The universe is not always intuitive. Our everyday experience is a classical approximation of a deeper, fundamentally quantum reality. At its smallest scales, the universe operates on rules that defy common sense, and that's perfectly okay. Observation matters. The act of measuring a quantum system irrevocably changes its state, turning potentiality into reality. Interconnectedness. The quantum world reveals a profound interconnectedness, exemplified by entanglement, where once interacting particles remain linked regardless of distance. Probabilities are fundamental. Determinism, in the classical sense, gives way to inherent probabilities, meaning the universe plays dice. Applied power. The weirdness of quantum mechanics is not just theoretical. It's the engine behind lasers, transistors, medical imaging, and the promise of quantum computing. The quantum journey continues. Scientists are relentlessly probing the boundaries of quantum mechanics, searching for answers to lingering questions, and pushing the frontiers of what's possible with quantum technologies. The nature of quantum gravity, the precise relationship between quantum mechanics and consciousness, and the possibility of discovering new particles or forces all remain tantalizing mysteries. As you navigate your daily life, take a moment to reflect on the quantum dance happening all around you and within you. Every atom, every electron, every photon is participating in this fundamental cosmic ballet, governed by the strange yet beautiful laws of quantum mechanics. We may not have a complete answer to what it all means, but the very act of asking the question and the scientific pursuit of the answers reminds us that the universe is far stranger, more wonderful, and more mysterious than we could ever possibly imagine. And that, in itself, is a truly amazing discovery.